Good morning, everyone. You're eagerly working on your homework. Is that true? Or more likely, you are not working on it yet because it's not due until Tuesday, right? And you probably have 3 other homeworks to do. Although I know at least one member of our class who only has 1 class. Of course, he also has a presentation tomorrow, so that gives him partial offsetting commitment. And everyone's going to Kevin's presentation, right? What time is it?
Yeah, I'm presenting lunch tomorrow. Not sure.
Yeah. But you want a big audience, right?
Yeah. Why not? A lot of critics.
And they're serving lunch? Is that true?
Yeah.
Is it pizza or what is it?
I think it's a nosh.
Depends on how you feel about that. But the talk is going to be great. Okay. Any questions? Do we have any questions about aeroelasticity? How many people watched the Duke basketball game on Tuesday night? So you did. Okay, good. Oh, you get extra credit. Okay. That's great. Who won?
We won.
Oh, okay. I just want to make sure you actually won. All right. Very good. Last time we had talked about doing gust analysis and also flutter analysis. And I quickly, in 10 or 15 minutes, covered everything that needs to be covered. But I had the impression that there were some glazed looks here in Durham, possibly in Stockholm as well. So I'm going to back up and do it again a little more slowly, because there was a lot of, I mean, if you understood everything that was said the other day, that's fantastic. But there was a lot in there that you may not appreciate all the subtleties. So remember what I did. I said boldly that within the framework of linear model analysis for aeroelasticity, the equation of motion for the structure is always of a certain form. And that form is the generalized mass, which we'll define in a moment, times some quantities that involve the generalized coordinate q, dots denote time derivatives. Here's the inertia term. Here's the damping term, where the zetas are made up entirely based on vast experience or not so vast experience, plus the stiffness term, which for linear elastic systems can always be expressed in this way, which is quite remarkable if you think about it, equal to a generalized force. So the generalized mass, and I'm thinking of a plate-like element, or at least a planar element, is defined as the integral over the area of this 2-dimensional object of the mass per unit area, which actually might depend on x and y, and might depend on the coordinates x and y, times these wonderful functions squared, dx, dy. And those functions are the functions in which we choose to express the deflection of this 2-dimensional object, plate-like object, in terms of a series, where the qm are the functions of time, which we hope to determine by solving this equation, times these wonderful functions of x and y. And this compact form is dependent on choosing those functions to be the Eigen Modes of the structure. If you don't know the Eigen Modes of the structure, you have to have a friend or a method, or both, to find them, okay? But that's a course in structural vibrations. How many people took Dr. Kielp's course in structural vibrations? Okay, so talk to these people. But so you can think of this as one of 2 ways. You need to take that course, which is a good idea, or you need to accept the fact that there are people in the world who know how to compute eigenmodes of structures. And the good news is that this is such a important thing that there are all sorts of software companies who will be happy to sell you a piece of software. You're probably using the finite element method to do that. Okay, now the Q sub m are the generalized forces, and in our case, they're due to the aerodynamic loading. They're due to an aerodynamic pressure acting on the structure. I'm going to call it delta P, which of course in general depends on X, Y, and T. Delta P because there's a pressure on the top of the wing, and there's a pressure on the bottom wing, and this is the pressure difference across the wing, times these Eigen modes, dx dy. And since we're integrating with respect to dx dy, by the time we do the integral, these q's only depend on time, right? But in general, there are two kinds of pressures and two kinds of generalized forces that are of interest. They're the pressures due to the motion of the structure. Those are essential to predicting flutter, right? But they're also important for gust response. Plus, there's the pressure due to the gust itself, okay? And within the fragment or linear model, we simply assume that these can be added together to give the total pressure of interest. So we have a pressure due to the motion, and we have a pressure due to the gust. I should give these some more numbers, I suppose. And to simplify things for the moment, we're going to assume that the Mach number is high enough, supersonic Mach number, that we can use something called piston theory. And for those of you who are hanging in for the last half of the course, we'll talk about where piston theory comes from. But for the moment, think of it as some aerodynamic friend. You have structural friends, you have aerodynamic friends. In this case, it's an aerodynamic friend tells you this is the thing to use at high supersonic flow. High meaning the Mach numbers 2 or greater, but not too high. If it gets up to 10, then that's hypersonic flow, and you have to do something else again. High, but not too high. And so it's equal to minus the density of the fluid times the speed of sound of the fluid times dw dt plus u infinity dw dx. And the gust velocity, gust pressure, is equal to minus rho infinity, A infinity, times the, actually a minus sign, although it doesn't matter, it turns out, minus what I'll call the gust velocity. So you can think of WG gust as being a gust displacement or displacement of a particle fluid with the dot, or if you prefer, dWg dt is the velocity of the gust. By the way, in the book, just to maintain a certain alertness on your part, and so you will not be a slave to the notation. In the book, I called W the displacement plate Z, okay? Because I want to use reserved W. Aerodynamicists think W itself is a velocity in the vertical direction. So one of the challenges of aeroelasticity is aerodynamicists have developed their own notation over the years, and the structural people have developed their notation over the years, and they didn't talk to each other until relatively recently. So, sorry about that. I didn't mean to damage the system. Okay. But you'll understand what we're talking about. By the time you get to the Q's, it doesn't matter, right? Everyone agrees on Q. Except, of course, the aerodynamicists think that Q is dynamic pressure, but you'll never confuse dynamic pressure with the generalized coordinate of the structure. It's all about context. Okay, now, so that's the basic idea. Now, I'm going to talk about a couple things that I didn't talk about the other day. I want to talk about where equation 1 comes from. And then the second thing I want to do is I want to expand on what the content of equations 4 and 5. And then finally, we're going to end up with a set of equations for the Q, which have only the gust velocity and the Q in them. And those equations we're going to use to compute a flutter condition or a gust response. But let's talk about equation 1, because I'm not sure we've actually talked about that in sufficient detail. So let's talk about where does 1 come from? Well, the first term, mq double dot, is fairly easy. It comes from the kinetic energy. Remember, the kinetic energy is 1/2 mass times dw dt squared dx dy. Okay? This is 6. And so if we take equation 3, which expresses w in terms of the q, we can write this in terms of the q's, right? So we can do that. So let's do that. There's a qm dot psi m sum over all m. This m is an integer. It has nothing to do with that m, right? But you're not confused by that. Times is squared. So this, I have to take this sum and multiply it by another sum. That'll give me a double sum, but I don't want to get confused on the summation indices, and therefore I better use a different indice. So summation over n, qn dot, psi sub n, dx d1, right? Thank you. And now we're going to rearrange this so that the only thing that depends on dx, x and y are the size, right? The q's don't. So I can take this 1/2 double sum over m and n, qm dot, qn dot, and now it's a double integral of m psi sub n dx dy. But now here's where the Eigen Modes come into play, and that's why we almost always use Eigen Modes for flutter analysis and aeroelastic analysis. It'd be nice to use orthogonality. And the Eigen Modes are orthogonal. They're not the only modes that are orthogonal in the world, but the Eigen Modes are always guaranteed to be orthogonal. That is, this integral is 0 unless these two indices are the same. So if we use orthogonality, then this double sum reduces to a single sum, and I'll make it a sum over n just for fun. I can use m or n, it doesn't matter. qn dot squared m sub n, where m sub n has the same definition that I had above, except I'm using the index n, m psi n squared dx dy, right? And now if I put that in Lagrange's equations, remember Lagrange's equations, you take partial t with respect to q and dot. You remember this. I mean, this is the most important thing in real life to remember. You do that, and that when I take a derivative with respect to q and dot, I get 2. That cancels 1/2, and I end up with q and dot. And then there's a ddt, and that gives me the double dot. So that's where that term comes from. Okay. So if I use Eigen Modes, I have orthogonality. I can always generate a term like this. This term, of course, I make up, so you can't dispute that. This term, you may or may not be quite, it's a little bit more difficult. It turns out that for any linear elastic body, this is still correct. But it's probably at this stage, thank you, yeah, this term I'm talking about. At this stage, it's probably better for you to do a couple of examples. The simplest, there are 3 examples you could do based on what you know in this course. One is you could do bending of a beam and prove that the bending modes of a beam have this property. You could also do the torsion modes associated with the beam rod and prove that they have this property. That wouldn't be too difficult. That's a good question for the final exam. Then you could also use the plate theory, if you remember what the plate theory looked like, and prove it's true for an elastic plate. And this is true for any shaped beam, any shaped plate with any variation in mass or any variation in stiffness. You can prove that this is true. Now, to prove it for a general linear elastic body, I'm actually not aware of any textbook that does that, but it's true. So you have to go back and look at the stress strain relations, the general equilibrium relation in terms of stress. If you did that, it's still true. Okay. And I think the person who generally credited for first doing this was a fellow named Maxwell of electromagnetic theory. He also worked on the elasticity in his spare time. And so there are all sorts of Maxwell theorems, and this is one of them. He also did acoustics. That was, I guess he did acoustics on Sunday, elasticity on Saturday. Worked on electromagnetics, magnetic, probably the rest of it, which is what he's probably most remembered for, but he did a lot of other good things too. Okay, so I'm going to briefly do it for the bending of the beam. Why? Because that's the easiest case. Okay, and then if you are skeptics and don't believe this is true, I invite you to do it for those other cases. Or you might have a chance to do it in the final exam. Okay. So let's do that. Remember what the equation of motion of bending of a beam looks like the following. It's when, if you will, it's when W no longer depends on X, Y, and T, but only depends on Y and T, right? There's no bending in the X direction. So we're talking about a beam. In the equation of motion, if you write down, well, let me back up a little bit so you can do this in the, I'm going to skip a few steps as you might imagine. The kinetic energy of the beam is just 1/2. I'll call it M, and I'll introduce D here just to make it a little more consistent. And now it's dx. What's B? B is the width. That's the dimension in the y direction, right? So MB is now mass per unit length along the beam, where M was mass per unit area, right? Okay. But more importantly, perhaps, U is 1/2 EI, that's the bending distance of the beam, second derivative of W with respect, oops, I said Y, didn't I? Sorry about that. Okay. Now, I take this and I put it in Hamilton's principle, all right? Okay. Okay. All right. And when you do that, I see I'm skipping a step, but I know you can do it. When you do that, here's the equation of motion. Secondary with respect to Y of EI. Note I'm letting EI still depend on Y. I don't need to assume it's constant. Plus MB secondary with respect to time equals 0. And I also get some boundary conditions. It will turn out that this result is true for any set of boundary conditions. I don't have to assume any particular boundary conditions. Okay. So this result is pretty general. Now, I want to find, what do I want to find? I want to find those magic modes, right? The Eigen modes. And to do that, I take W as a function of Y and T and assume it's of the form W, I'll call it bar, of Y, e to the I omega T. When I find the magic values of omega, those are the resonant frequencies of this beam, the corresponding functions of Y are the Eigen modes. So I can also write this in this notation, psi m of Y, thank you, e to the I omega mt, where m is any integer corresponding to any mode of interest. And again, I probably should use some equation numbers here. Let's call it 7, 8, 9, 10. Okay. And so what do we have? We have if I put this in, then I have, again, the second derivative. The E omega t term is going to cancel out, right? And the second derivative of time is going to generate a factor I omega squared, right? Otherwise known as minus omega squared. So I'm going to have this. Minus omega m squared mb psi sub m equals 0, right? So okay. Still with me? Now, let me tell you what we're going to do before we do it. Here's the idea. We can prove orthogonality. I think I actually did this, so I'm not going to do that again. We can prove orthogonality by writing the same equation with, say, omega n and psi sub n, and then we multiply this equation by psi sub n and integrate over y, and this one by psi sub m integrate y, and we prove orthogonality. We did that, right? I think we did that. So orthogonality is, in this case, mb psi sub m psi sub n dy is 0 for m not equal to n. And also, you have to integrate by parts a little bit, but you have ei second partial of m with respect to y, second partial of psi sub n with respect to y, dy. That's also 0 for m not equal to n. Okay, we did that, right? Thank you. So we did that. So what else can we do? Well, once we know that, then we can take just this equation and multiply by psi sub m, the one that's not ortho. Right, this is, we're not going to use orthogonality now, right? So we can multiply, I'll just call those 13. Multiply 12 by psi sub m and integrate. Now what are we going to get? We're going to get second partial ei second partial and psi sub m integrated with respect to y. Got a minus side, I'm going to take it on the other side just because I know where I want to go, equals omega m squared mb psi sub m squared dy. Right? Now, why is this a wonderful thing to have? It's a wonderful thing to have because when I take equation 9 and express W in terms of these Eigen modes, I'm going to get something that looks a lot like this. In fact, it's going to look almost identical to this. And I'm going to use this result to write this in terms of omega m squared and the integral over mass. That's what I'm going to do. Okay? Well, let's see how that works. Let's go to 9. Let me remind you what 9 is.
Oh.
Okay? All right. Okay, let me just remind you what equation 9 was. It was EI 1/2, of course, second derivative of W, E1, okay? But now I'm going to take W and write it as this modal series, QM times the magic modal functions. Right? And I won't even give this a number because it's so familiar you'll never forget it, right? I'm going to take this equation, put it in here, and then we'll get, I guess we're down to 15 now. 1/2. Again, we're going to get a double sum, right? We're going to get a sum over m, let's say, qm, second derivative of psi m with respect to y, times, sorry, I didn't leave myself enough room, another sum over n, qn, second derivative of psi n with respect to y, dy. But now we're going to invoke the other orthogonality property, right? So this double sum will reduce to a single sum because of orthogonality. U is just 1/2 single sum of qm squared ei okay, squared. And what I had in 14, let me write down 14 again. What I had in 14 was this. Wasn't quite that, but it was close. That was 14. Okay? Well, it turns out this and this are the same, obviously. Why is it obvious? Because if I integrate by parts twice, I'll have an integral that becomes this. Remember, each time I integrate by parts, I'm getting a minus sign. I do it twice, the minus signs will cancel. I'll have some tail terms, but all those tail terms will be 0 because of the boundary conditions that are permissible. Whatever boundary conditions you have, something in one of those tail terms will be 0 at each boundary, right? And therefore, this is equal to that, but then this is equal to this, and therefore that is equal to this, which is what I wanted to prove, right? So when you have these potential energy terms, they can always be written in terms of the natural frequencies and the generalized masses. And this is a particular case, but to my knowledge, no one's ever found a case where that's not true. And Maxwell allegedly, in some obscure paper in 1890 or whenever, probably in the Proceedings of the Royal Society, proved it for a general linear elastic body. Okay. So that means that the potential energy can always be written as 1/2. Of course, it's a 1/2. Summation over m, q sub m squared. Omega m squared m sub m, where this is the generalized mass, and for the beam in particular, this generalized mass is just this integral m, the mass per unit area, times the width of the beam, which makes it the mass per unit length, times the mode shape squared dy. So now we've dealt with the structural side of the equation, and I'm trying to convince you, not completely rigorously, but at least very suggestively, that what we had a few pages ago namely this, is always true for any linear elastic body. But finding the magic modes is a non-trivial task. I mean, people earn a living by doing that, right? And that's okay. That's a good living. It's a wonderful thing to do. But you don't need to be an aeroelastician to do that. So normally you leave that to somebody else, or at least to somebody else's software. Okay. I'm going to pause now. Any questions about the structural side of the model? Because now we're going to deal with the generalized forces and the aerodynamics. Stockholm, are you okay with the structural side of the equation, this side of the equation? Because now we're going to do something with the right-hand side.
Yeah, we're fine so far.
Okay, good. I'm happy for everyone. Okay, let's now look at the aerodynamics. Now, I swept something under the rug. I don't know. There's probably something like that in Swedish. Anyway, let's look at this aerodynamic side of the model now. Aerodynamic model. And remember, there are two pressures. There's the pressure due to the gust and the pressure due to the motion. I'll do the gust first, which is the easier thing, but I'll even do the one on the motion. The one for the gust is minus rho infinity, A infinity, minus the gust velocity. I'll put a dot there. And then we want to know what the generalized force is due to the gust. And by definition, it's the pressure times the mode shape, dx dy, right? Well, that's pretty easy. It's just then minus rho infinity, A infinity. And if you want to, you can allow the gust to vary over the wing, right? It could be a function of x and y as well. Often people assume it's not, but you could allow it. Then double integral of wg times this mode shape dx dy. Someone has to tell you what the gust, someone has to tell you, or you have to divine by some means what you think the gust velocity is. And often it comes from a combination of flight measurements and a little bit of curve fitting. And there is a little bit of theory based on the theory of turbulence. We won't discuss that later, right? Do I need a dot? Thank you. Need a dot. Okay, so that takes care of that. So then let's look now at the part due to the motion. Of course, that's delta P due to the motion. I should put a gust here, I suppose. Psi sub m dx dy. But remember, delta P to the motion is minus rho infinity, A infinity, dw dt, plus U infinity, dw dx. Right? This is the actual velocity of the wing moving up and down. This term is an equivalent velocity, if you will, due to the fact that there's a mean flow U infinity. In fact, you can get this extra term by moving from a coordinate system fixed with respect to the fluid to a coordinate system fixed with respect to the wing, but we won't get into that yet. That's another good question for a final exam or preliminary exam or something like that, qualifying exam, something like that. Okay, so this is due to the motion. But remember now, but recall, W is equal to the sum over, and I want to distinguish between various mode shapes. So I'm going to make this a sum over n, so I won't get confused with that m. Qn psi n, right? W has contributions from all the modes. Therefore, this pressure due to the motion has contributions from all the modes, right? Therefore, even though this is the generalized force associated with the nth mode, first mode, the second mode, and the third mode, the generalized force in each mode has a contribution from all the modes due to the aerodynamics. So even though we used Eigen Modes for the structure, which was nice because orthogonality meant we could look at one mode at a time as far as the structural terms, when you get the aerodynamics, the modes are going to be coupled anyway. Sorry about that. But nothing to be done about that. Well, in principle, you could. You could actually find the aeroelastic modes, okay, and invoke orthogonality again, but no one ever does that because by the time you found those modes, you solved for the flutter solution. So why bother? Yeah. Anyway, okay, let's move right ahead. So we have this. We're going to put this in here. Let's see. I should give this some decent numbers too. 15. Let's see. 16, 17, 18, 19. Again, this is your favorite equation of all time, so I won't even bother to number it. So we take this, put it in 19, and what do we get? We get delta P due to the motion is now minus rho infinity, A infinity, summation over n of q sub n dot times psi sub n, that's this term, right? Plus q sub n times d psi n dx, that's this thing. Okay? And now we take 20 and put it back here, and we get q sub m due to the motion.
There's velocity.
Do I miss something? What do you want?
U infinity on the second.
Oh, did I lose? Well, that's important. Thank you. I did not mean to shortchange you. Thank you. So now we have, what do we have? We have minus rho infinity, A infinity, they're constants, so we can take those outside. There's a summation over n. We have a qn dot, integral of psi n times psi m dx dy plus u infinity qn times integral of psi n dx psi m dx dy. Okay. So that's our generalized force in the nth mode due to the motion, but it involves terms from all the modes. And so be it. So be it. So now we can actually solve a problem. Because now if we take these results, I guess I'll pose this 21. If I take 21 and I take 17 and put them into equation 1, which was the equation of motion for the structural modes, I have equations which in principle I can solve for these coefficients, the q, the small q. And I can solve for gust response, and I can solve for the flutter condition. And we got time to do at least some of that today. But let me pause now again. Questions? Concerns? Issues? Stockholm, any questions?
No questions.
Okay, yes. Which one?
Should these be double integrals?
Double?
Should this integral be a double?
Oh, I thought double integral. Yeah, I didn't mean to shortchange you. I'm sorry.
And the one below,
Yeah. Yeah. Yes, absolutely. Integral over the dx and dy. Okay. So let's spell it out a little bit. Let's look at the first mode, right? Then maybe we'll look at the second mode. and then leave it as an exercise for homework to look at a larger number of modes. Okay, so let's look at the first mode equation. Let's see. It's what? It's m sub 1, p sub 1 double dot, and so forth. Only properties of the first mode appear in the first mode equation as far as the structure is concerned. But then on the right-hand side, we have Q1 due to the gust plus Q1 due to the motion. And this is, what was it? Rho infinity, A infinity, double integral of the gust velocity dx dy. And this was what? It's minus rho infinity, A infinity. It's a summation over n of qn dot, the double integral of psi n, psi 1, because we're looking at the first mode, dx dy, plus u infinity, qn, oh, sorry about that, d psi n dx, psi 1, dx dy. Okay. Yeah. Which line don't you like?
In the middle of the page, Q1 gust to throw out the W dot G psi.
You don't like the gust term or the other term?
The gust term.
What's wrong with the gust term?
Psi inside of the summation.
Oh, I'm sorry. I left out the mode shape, didn't I? Thank you. Psi 1. Thank you. In fact, let me redo this. Yes, that would not be quite right. Sorry about that. I got too excited. Okay. Now, and we could do a second mode too. I think just looking at this will let us do a couple of things. There are some special situations that I'd like to highlight for you. Let's look at this term. Let's look at this term for just a moment. If I had a constant mass distribution, right? If I had a constant mass distribution, then orthogonality would be, I could take the mass outside, and orthogonality would say this integral is 0 unless n equals 1, right? Well, if it's not exactly a constant mass distribution, but the mass doesn't vary too rapidly, this probably suggests that the dominant term in this series is the term when n equals 1. And if you look at this, this is qn dot, right? And it's a minus sign, but it's on the right-hand side of the equation. So if I put it on the left-hand side of the equation, that gives rise to a damping-like term, right? Damping-like term. And often in aeroelasticity, it's the aerodynamic damping term that overwhelms the structural damping term. In fact, it's not uncommon to set the structural damping term to 0, unless you really need it. Really need it, meaning you're on the ragged edge of having flutter. And to convince the authority that's approving your airplane design that you really have enough flutter margin, maybe a little structural damping will boost it up, your predicted flutter speed high enough that you think you're okay. Actually, if you're that close, you do a flight test. But you see what I'm saying? Normally, you're not too concerned about the structural damping unless you're really right on the ragged edge of getting fluttered, and then you might agonize about it. Another thing is if this gust distribution has a spatial distribution that looks like one of the modes, anyone, say the first mode, well, then there will be a very powerful effect because this will be like some constant times psi 1 squared. On the other hand, that means the gust won't excite the other modes very much. So the gust distribution can be important, right? If there's a matching between a mode shape and the gust distribution, that mode is going to be excited more, all things being equal, than some other mode. And then finally, this term is kind of interesting. Well, let's look at this term for just a moment. And yeah. Let's look at the special case when n equals 1. Right? I mean, there are a lot of terms, right? There's a summation of all modes. But let's look at the term in the summation, which is the same mode as the equation of motion we're dealing with at the moment. If I have, and since this is derivative with respect to x and I plan to integrate by parts, I'm going to forget about the derivative, the integral over y. If I have this integral, what's that equal to?
Psi 1 squared.
Psi 1 squared. Maybe a 2 down there. Yeah. Evaluate the limits. X equals 0 and up to x equals chord. Chord meaning, you know, how far back we go on the wing. If it turns out that this mode shape is 0 at the two endpoints, then this term is 0. For a real airplane, for an airplane wing, that's not likely to be true. But if you have a panel, you know, a little skin panel on the wing, if you ever look at the wing and rivets and all that, those panels are typically constrained at the leading and trailing edge. Those panels have mode shapes where this is 0 at the leading and trailing edge. So in panel flutter, so-called, this term actually is 0 for the same mode, which means that this term doesn't contribute at all. On the other hand, the n equal 2 mode is critical, all right, because that gives you a non-zero result. Because while it's true that the modes themselves are orthogonal, the derivative of one mode is not orthogonal to the function of a different mode. So it's the so-called off-diagonal terms from this contribution that often generate the flutter mechanism, not only for panel flutter, but also for wing flutter. So there are some things that you can anticipate. Of course, I'm relying on the fact that I've done a few of these calculations in the past, but if you look at the equations, they can tell you something about which mode is likely to be most important in terms of the gust input, which mode is likely to be most important in terms of generating damping, which mode is likely to be most important in terms of generating water. Okay. Yes.
I don't know if you explained this right, but the gust velocity there, that's just an amplitude, isn't it? A very refined unit sustainment per second.
Well, the gust
W dot G.
W dot G has the units of velocity, yes.
Meters per second.
Meters per second, feet per second, inches per second. Yeah, one of those.
Is that the same for every mode?
No.
No.
Well, what do you mean by saying the gust velocity is the gust velocity doesn't know anything about the modes.
Right.
The gust velocity is there because there's a random motion of the fluid in the atmosphere, and then an airplane comes by, which has some modes. But the gust velocity doesn't know anything about modes, except that when I'm interested in which mode does the gust excite in the structure, then if the spatial distribution of the gust velocity tends to match well with the structural mode, then that mode will get more excitation than some other mode. But the modes of the structure don't change the gust velocity. It's there. But I might choose, I mean, just to make the, bring out paper here. Yeah, thank you. So the gust velocity in general depends on X, Y, and T, right? And it's there. Someone measured it. Someone who's an expert in meteorology told me what it was, whatever. But I could choose, if I wanted to, I could decide that I want to represent the gust velocity in terms of a series of nice functions. And I might choose the Eigen modes of the structure. Why? Because I am interested in how well the gust velocity distribution matches the Eigen mode of the structure. So I could write this as Qn sub gust. These are not the Q's associated with structural motion. This is just a representation of the gust velocity field. If you want, I'll put a dot over here to indicate I'm talking about velocity. I could do this. I could do that. That might be interesting because looking at the coefficients of this representation, that would tell me which modes in the structure are most likely to be excited by that gust. Did I tell you what you wanted to know, or I told you more than you wanted? Okay. Okay. Now, since you raised this question, how do I find those coefficients? I'll make it easy for you. How do I find those coefficients if the mass distribution is a constant? If the mass per unit area is a constant, how do I find those coefficients? What wonderful property of these mode shapes would I use? What is the most wonderful property of all Eigen modes? Orthogonality. Okay, so I could multiply. I could multiply by some other mode. I don't want to multiply by the nth mode. I'll multiply by the 17th mode, right? This goes from 1 to 29. I'm going to multiply by the 17th mode. And I'll do this. And I have to have a double integral, right? And then on this side, I'll have the summation over n, Qn dot gust, integral of psi sub n times psi sub 17 dx dy. What's that integral equal to for a uniform mass distribution? It's 0 unless n equals 17, which means I only have the Q17 term surviving, so this tells me what the Q sub 17 coefficient is. And I do the same thing for any old other mode, and I get that coefficient. So if I wanted to, if someone tells me what the gust distribution is, I could represent it in terms of mode series, in terms of structural modes. But that's just a convenience. It's not that the gust is determined by the structural modes. It's just that that's a convenient representation, because my interest in the gust for aeroelasticity is not in the gust itself. I mean, there are people who, the meteorologists who are worried about the gust for its inherent sake, right? But I'm only interested in how it excites or doesn't excite some of the structural modes. So this representation might actually be useful. So that's a good question. Thank you. Yeah, good question. Okay. What else we want to do? Yeah, we got a little more time. So let's complete our gust analysis in a moment. And in the spirit of getting on with it, we'll just use one mode, right? In fact, often in preliminary design, I don't know if that's true. Often in preliminary design work, they only use one mode to do a gust analysis. Now, you have to use the right mode. If you usually, it's either rigid, well, if it were a cantilever model, I'll make it easy for myself. if we're a cantilever mode, you probably use the first bending mode, because that would be the mode that's most likely to respond to the guts. If you want to do the real airplane, you probably have to use rigid body translation as well as maybe first bending. You might have to use two modes. Yeah, the heave mode plus first bending. Yeah, but using gust analysis, you don't need a zillion modes. A relatively small number of modes work. Unlike flutter, where you may have a lot of modes. Why? Because you don't know if the wings on the flutter, or the horizontal tail, or the vertical tail, and maybe the fuselage gets involved too. And so one reason you use a lot of modes in flutter is because you're not sure a priori which one may be the problem. In fact, I think more often it's a control surface, right? Yeah, at least in terms of by the time you get to flight test. I mean, it'd be a little embarrassing for your wing flight, but there are enough uncertainties about your control surface, particularly in terms of aerodynamic representation, that it would not be unknown that even an experienced aeroelastic team might predict that everything's going to go just fine, and then you go out and flight test or wind tunnel test, and you find that one of the tail surfaces has a little bit of an issue that you need to do. Okay, so let's just use one mode. One mode. Well, if one mode, we just have this equation, which I'll write down one more time. Thank you. And now we have equal, the gust is this. And then the part due to the motion is this. Well, we only have one term surviving, so we only have one mode. So we have Q1 dot double integral psi 1 squared dx dy plus U infinity Q1 there it is. I'm going to call this 22. So what do we have here? Well, this term, this term is just a damping term, right? So I'm just going to probably add it to that, and it's a combination of structural and aerodynamic damping. This term is not zero unless those modes have special properties that we discussed a moment ago, but probably isn't terribly important as it turns out. And of course, this is really important in gust analysis because this is the gust, right? There's not much gust response if you don't have a gust. So, okay, all right, okay. So,
Thank you.
you're welcome. Let's look now at various kinds of gust representations. One is a so-called sharp edge gust. Sharp edge gust is one where it has, if I plot WG dot versus time, and this is t equals 0, the gust is 0, and then it's a step function, right? It's a step function. And since this is a linear system, if you know about linear systems, if you find the response due to the step function, you can in principle use that to find response at for any other input. Or you can just keep solving this equation. But if I have a step input, what do you think happens at very large times? What happens at short times? get oscillations. Do they damp out? Yeah, they damp out. And then what happens at very large time? Well, if things damp out, this term goes away and this term goes away, and I get a Q1. But Q1 just means I've displaced the airplane, right? it's just a static solution at large time. And what bothers people's stomachs and might possibly be an issue in terms of fatigue for the structure is the oscillations. Right? So the long time static displacement is usually not the primary concern. On the other hand, if we had a random input, to go to that extreme, what are we going to do if we have a random input? What if we represent this gust velocity as a random input in terms of its power spectrum? Yeah. What was that wonderful? Here's what we said the other day. Random gusts. I'm going to assume that someone tells me what the gust power spectra is. I guess we use a different symbol. Gust power spectrum. And I'll make it simple. We'll assume that the gust, the variation in space over the wing, okay? The gust itself has a spatial variation. But if it varies slowly in space or mildly in space over the wing, which is typically true, right? Then the gust field typically has a large length scale compared to the size of an airplane. If this is only a function of frequency and not a function of x and y, then if I want to find the power spectrum of, let's say, of Q1, and since I only have one mode, that's equivalent to finding the power spectrum of the plate displacement, right? How do I write that in terms of power spectrum of the gust? What do I need to know? What do I need to know here? What is that thing I need to know? Call? Transfer function. I need to find the transfer function. I need to find a transfer function that takes me from WG dot to Q1. And where do I find the transfer function? Well, I would find it from equation 22. So you should do that as a homework problem. But we'll wait and sign that the next time. We're going to see the homework is going to be due Tuesday, right? So, but this is a preview of the next homework problem. And once you have that, how are you going to find the mean square of Q1, which is equivalent to find the mean square of the deflection? What are you going to do with the power? What are you going to do with this power spectrum? We're not sure. Well, I'm going to integrate it over all frequency. Okay? And when you try to do that, you may run into some difficulty. But I will not reveal the difficulty just yet. We'll save that for later. Okay. So we have an equation of motion. We've included the effects of the motion on the aerodynamics, at least within the framework of piston theory. We've included the effect of the gust, otherwise we can't do a gust analysis. If the gust is represented by something simple like a step function, we just integrate it. Actually, in this case, you could probably integrate it analytically, but you can certainly do it with the computer, right? Or if it's a random input, you probably will go to power spectral density analysis and find the transfer function, which means you're going to let the gust temporarily pretend to be sinusoidal in time for the purposes of finding the transfer function. Mhm. And then you're going to square it, multiply by the input power spectra, find the output power spectra, integrate that over the frequency, and then you'll be done. Okay. Any questions before we conclude for the day? Here in Durham, North Carolina. Any questions in Stockholm?
Any question?
No, thank you.
Very good. Thank you for your patience today. We'll see you all on Tuesday.